question bank discussion? Let me know. So,
Module 1.
huh?
Module 1 is
Module 1.
Module 1 నుంచి చెప్పండి సార్.
Already sir will discuss now about the question bank of module 1 and module 2. Sir discuss chesara lera?
Not clear, sir.
So coming to the part, I think analytical question no need to discuss. I think, is it necessary to discuss about the analytical questions also? Is the PPT is visible, Amma? First thing is PPT is visible to everyone. Four 462. ఎవరైనా ఒక్క రెస్పాండ్ అవ్వండి. Yeah, okay. Okay. Now coming to the module 1, analytical questions is necessary to discuss. Is it necessary? So anyway, I am going to discuss about the module from module 1. So coming to the module 1, so first thing is calculate the velocity and kinetic energy of the electron having wavelength of 0.21 nanometers. Before that, so I repeat the formulas which we are used to solve the problems from the module 1. So first one is, wait. Yeah. Calculate the velocity and kinetic energy of the electron having wavelength of 0.21 nanometers. Again, I stop the sharing in, wait, Amma. Wait, Amma, hold on 1 minute. Okay, it is coming. But Yeah. So first thing is calculate the module 1 question bank number. Calculate the velocity and kinetic energy of electron having wavelength of 0.291 nanometers. So wavelength is given. So use the formula of lambda equals to h by m into v. All of you try to find out the velocity. After that, using the formula kinetic energy equals to half m square. Find out the kinetic energy also. So before that, so there is no option to write the formulas here directly. That's why I'm searching for that option, but it is not showing. Design layout. Yeah. సార్ ఇది ఒక 1 సెకండ్ ఒకసారి వస్తుంది, బట్ ఇది నేను పీపీటీ షేర్ చేశాను.
యానోటేషన్స్
లేదు
ఉంటుంది మోర్లో మీరు డ్రైవర్స్ డౌన్లోడ్ చేశారు.
wait for 1 minute, all of So welcome back, Andy. Sorry for inconvenience. Because of that, writing option is not there. I'm searching for that one. So coming to the formulas which we used in the module 1 is wavelength formulas. First thing is, first one is lambda equals to h by m into v. And second one, lambda equals to h by p. And wavelength, lambda equals to h by root over 2me in terms of kinetic energy. And fourth one, in terms of applied potential, lambda equals to h by root over 2m e into v. Capital V is applied potential. In case of electron, it is 12.26 angstroms by root v. We know that these formulas. So including that, we are using energy formula also to solve the problems. E suffix n equals to n square s square by 8ml square, where n is a quantum number, h is a Planck constant, and L is the width of the potential well. And these are the formulas we are using to solve the problems. 1, 2, 3. We don't have problem on the lambda equals to h by p momentum. These 5 formulas only we are using to solve the problems. Now I'm going to the problems now. Coming to the second one, determine the de Broglie wavelength associated with a proton moving with a velocity of 1 by 10 velocity of light. So your velocity is given. Velocity is given. Amma 55. What happened? De Broglie wavelength associated with a proton moving with a velocity of 1 by 10 velocity of light. So 1 by 10 velocity is given. Velocity equals to 1 by 10 into velocity of light, nothing but 3 into 10 power 8. So velocity equal to 3 into 10 power 7 meter per second. So mass of the proton is given. So de Broglie wavelength in terms of velocity, lambda equals to h by m into v. Using that formula, by substituting Planck constant, m mass of the proton also given, velocity 3 into 10 power 7. So by substituting the 3 quantities, all of you try to find out the wavelength. Already we find this wavelength. That formula is, sorry, wait. Right. So coming to the estimate the wavelength of an electron, rise to a potential. Rise to a potential of 15 kilovolts. So converting into the volts, by converting into the volts and using the formula here, electron is given. In case of electron, what is the formula to find out the wavelength? Lambda equals to 12.27 or 26 angstroms by root v. Using that formula, all of you try to solve the third one. Fourth one, obtain the de Broglie wavelength of neutron. So kinetic energy is given. So but here kinetic energy is given in 0.02 electron volts. So converting into the volts to while you are substituting kinetic energy in the formula. What is the formula we are using here? Lambda equals to h by root over 2 into m into e. We need to find out the wavelength, the kinetic energy, and mass of the neutron is given. So in terms of kinetic energy, what is the formula to find out the wavelength? Lambda equals to h by root over 2 into m into e. Capital E is the kinetic energy. Don't substitute directly 0.025. After converting into the joules, all of you try to substitute in the formula. That how we are going to convert? Anybody? All of you? Any one of you? How we are converting electron volts to the joule sum?
Okay. By 10 per
1.66 into 10 power minus 20.
By multiplying with charge of the electron, right? 1.6 into 10 power minus 19. We are going to convert electron volts from the electron volts to the joules. So that using that formula, lambda equals h by root over 2me, all of you try to find out the de Broglie wavelength also. And coming to the fifth one, calculate the wavelength of an proton if the kinetic energy of the proton is 500 electron volts. Again, one more formula, one more problem in terms of kinetic energy only. Here 500 electron volts is given. So proton mass, we know the proton mass also by substituting the proton mass and mass of the proton, and kinetic energy 500 electron volts. Again here converting into the joules. And sixth one, find the wavelength associated with a electron rise to a potential. Here rise, not rose, rise to a potential 1600 volts. Directly potential is given. In case of electron, that's why all of you try to use the formula 12.27 angstroms by root V. Okay, 12.27 angstroms by root V is the formula to solve the sixth one. So coming to the seventh one, calculate the energies that can be possessed by a particle of mass 8.5 into 10 power minus 31 kg, which is placed in a infinitive potential box of 10 power minus 9 meters. So what is the formula here? We are to find out the energies. En equals to square is the formula to find out the energies. So here how many energies we are going to find out here not mentioned. So that's why all of you try to find out at least 3 energies, E1, E2 and E3. So what is the relation between the E1, E2 and E3, Amma? Any one of you? Again, I'm asking the question, what is the relation between the energies E1, E2, E3?
E2 equals 4E1, E3 equals 9E1.
You're right. So E1 is to E2 is to E3 equals to 1 is to 4 is to 9. By substituting in the formula n equals to 1, we are getting the ground state energy level, nothing but E1. By substituting n equals to 2, we are getting the first excited state, and by substituting n equals to 3, we are getting second excited state, nothing but E2. So the relation is E1 equals to E2, E1 is to E2 is to E3 equals to 1 is to 4 is to 9, and so on. Using that relation, all of you try to find out at least 3 energies. So coming to the eighth one, find the lowest energy of an electron confined in a square box of side 0.4 nanometers. 0.4 nanometers, converting into the meters. So 1 nanometer equals to how many meters? 10 power minus 9 meters. So lowest energy nothing but n equals to 1, ground state. So by substituting n equals to 1, we are getting the formula E1 equals to h square by 8 ml square. So h is the Planck constant. That value is 6.625 into 10 power minus 34. And m is the mass of the electron. Electron is mentioned, the particle is electron. That's why mass of the electron you can take 9.1 into 10 power minus 31. And L is the 0.4 into 10 power minus 9 meters. By substituting the 3 quantities, find out the ground state energy. Eighth one. So coming to the ninth one, electrons are accelerated by 344 volts and are reflected from a crystal. The first reflection maximum occurs when the glazing angle is 60 degrees. So determine the spacing of crystal. So simple one. Using the Bragg's law, all of you try to find out the wavelength. Electron accelerated by 344 volts. The first order reflection maximum occurs at 60 degrees. Determine the spacing of crystal. So use the formula. Here see, I'm going to share the white screen now to solve that one, because there is no writing option. So potential is given as 344 volts. V equals to 344 volts. And first order reflection maximum is occurred. So we need to find out D. So 2D sin theta equals to n lambda. Formula is, so here theta equals to also mentioned 60. Glazing angle is 60. So lambda is we don't know. So electron is given and potential is given. So using the formula lambda equals to 12.26 angstroms by root V, all of you try to find out the wavelength. That equals to 12.26 angstroms by root 344. So we are getting the wavelength. So after that, to find out the d, so what is the formula? N lambda by 2 sin theta. So that equal to n equals to 1, lambda will be 12.26 angstroms by r into 10 power minus 10 r, keep it angstroms only, 344 divided by 2 into sin 60. So d value also you are getting in angstrom units. Try to simplify and get the answer number. Very simple one only. Now coming to the seventh, last one, I think. An electron is bound in a one-dimensional infinity well of width 1 into 10 power minus 10 meters. Find the energy level in the ground state and first two excited states. Ground state nothing but E1. E1 equals to h square by 8ml square. So after that, how can we find out the E2? E2 equals to, using the relation between the E2 and E1, find out the E2. So 4 in, using the formula E2 equals to 4 into E1 is the relation, and the E3 is 9 into E1. Same thing, similar to the seventh one. So these are the 10 numericals from the module 1. So coming to the part B, long answer question. Compare a particle with a wave and discuss about dual nature of radiation. Can any one of you please explain about the particle, or compare what is the difference between the particle and wave? Can you explain about the dual nature of radiation? Any one of you? No one. That's why I'm asked to discuss about the from module 3. Reverse lo vaddam anukunnanu. No one. What is particle and what is wave? Rule number 63. Are you there? 63? 65. Rule number 65. No. Please respond. If you know or don't know, that is a secondary thing. When I call your roll number, please respond. Say yes or no. (63) are you there, Amma?
Sir, yes, sir.
So what is the first question? Read it.
Compare a particle with a wave and discuss about dual nature of radiation.
Then what is part? How can you define the particle and how can you define the wave?
Sir, wave is the motion of the, it shows the motion of the particle. And a particle is an atom.
What are the differences? Compare the particle and wave. Give some points to compare the particle and wave. Only dual nature of radiation and ఏంటి? Discuss about how can you discuss about the dual nature of radiation when the question is asked in your examination?
Dual nature means wave nature and particle nature, sir.
How can you explain about the wave nature and particle nature? Dual nature means I am taken two examples. I am given two examples where the particle is acted as a wave and where the wave is acted as a particle. By taking two examples, I explained about the dual nature of radiation in the class. What examples I am taken? The photoelectric effect we are taken. Using the photoelectric effect, we explain about the dual nature of radiation. So in the photoelectric effect, what will happen? Electrons are ejected from the metal surface, right? When the sufficient energy, when the sufficient light energy falls on the metal plate, what will happen?
Electrons
from the metal plate,
ejected.
Electrons are ejected. Nothing but wave is acted as a particle. That is dual nature of the particle. At the same time, so wave is acted as a particle also explained by taking the one more example or one more theorem or one more experiment, that is Davison-Germes experiment. In that we are producing the waves, we are producing the electrons. When the electrons strike the nickel crystal, so wave nature we can explain. Wave nature of the electron we are explaining in the Davison-Germes experiment by taking the two examples. We discuss about the dual nature of radiation in the class. So that thing you have to write for the first question. So what is the second question number? Rule number 1. Rule number 1. Are you there? Rule number
Yes,
1?
sir. Yes, sir.
Yeah. Read the second question number.
Explain the physical significance of wave function according to Schrodinger and Max Born interpretation.
Yeah. What is the physical significance of wave function?
So, psi square is proportional to the probability of finding a particle, sir. Means
It is a-
normalization condition. New equation will find out.
Yeah.
Integration,
Yeah,
integral
it is a-
limit between infinity to minus infinity, psi square dx equals to 1.
If the particle is present,
Sir?
so the what is the normalization condition? Modulus of psi square into dx equals
Dx
to
is
1. If
equals
the
to
particle
1.
is present
Limits
in one dimensional, minus infinity
Yes.
to plus infinity. So actually, the physical wave function is a physical quantity. It has no direct physical meaning. It is a complex quantity. Means it represents both particle nature as well as wave nature.
Yes, sir.
So at the same time, if the particle is present, we are taken. If the particle is present, to find out the particle, we are using normalization condition, right? That only 1 or 2 points are enough to explain the physical significance of wave function. So that is actually short answer question. We are given in long answer. So don't expect these type of questions in the final examinations, except the mid examinations. Okay. So rule number 2. Rule number 2. Are you there, Amma? Rule number 2.
Yes, sir.
Okay. Read the third question.
Matter waves are new kind of waves. Justify this concept by discussing different properties of matter waves.
Yeah. Tell me the answer now.
Sir, by the equation lambda equals to h by mv, we can state the properties of the matter waves. Where the lighter the particle, the wavelength of the particle is greater. That where h and v are constants, and lambda is directly inversely proportional to the mass. And the second property is this, h and m are the constants where lambda is inversely proportional to the velocity.
Lambda is inversely proportional to velocity.
Where lesser the velocity, longer the wavelength will be.
Okay, good. That is the second point. But
Yes,
how
sir.
can you justify the concept of matter wave or new kind of waves?
Sir, I don't know that, sir.
That are the properties. Okay, good, very good. Coming to the third property about the velocity. If velocity
Yes,
equals to 0, if you are substituting in that formula lambda equals to h by m into v, what about the wavelength when velocity is 0?
Sir,
So
matter waves are only associated with the moving particles.
moving.
There's a
Right, good. That is
lambda will be
another
infinity.
point. But we can't say matter waves are new kind of waves using. Right. That is one more property. But we can't say using the 3 points matter waves are a new kind of waves. But using the fourth property, whatever we discussed in the classroom, using that property, we can say matter waves are new kind of waves because of fourth property about the charge. What is the fourth property about the charge of the matter wave? So
Yes, sir.
matter wave
They are independently
associated with,
charged, sir.
Independent of charge. So that's using that property, we can say that there are not electromagnetic waves, that matter waves are new kind of waves.
Okay, sir.
Because of electromagnetic waves are associated with only charged particles, but matter waves are associated with either whether the particles are charged particles or uncharged particles, matter waves are associated. So using that property, we can say matter waves are not electromagnetic waves, they are new kind of waves.
Okay, sir. Okay, sir.
Yeah. first to discuss about the fourth property. After that, if you have sufficient time to discuss about the
Remaining properties.
remaining properties also. Using
Okay,
the
sir.
fourth property, one or two, first to three properties na, about the velocity also. Matter waves can travel with more than the velocity of light. That properties we
Yeah.
can discuss, but mainly discuss the fourth property.
Okay, sir.
To answer the third question, all of you try to write on the first. Try to start with the fourth property.
Okay, sir.
Okay, Amma. So rule number 6. 6, Amma. Rule number 6.
Sir,
6.
sir,
What is the fourth question, Amma? Read the fourth one.
using Planck's and Einstein theory of radiation show that the wavelength associated with an electron of mass m and kinetic energy is given by h by under root of
By
2m.
lambda equals to root. Right, very good. So how can you derive the equation for lambda in terms of kinetic energy?
The Planck's
Clear
theorem,
using the Planck's theory and Einstein theory. What is the Planck theory?
lambda equal to h by m.
Is it Planck's theory? From the Planck's theory, we are taking the energy of the photon.
Okay.
What is the equation for energy of the photon? E equals to h nu or E equals to hc
Equal
by
to-
lambda. H nu or hc
Okay.
by lambda. And Einstein theory. What is the Einstein mass energy equation? From the Einstein theory, we are
Equal to
taking
mc
the
square.
E equals to mc square. By comparing the two equations, we are getting the equation for lambda equals to h by m into v. So after that, that m into v equals to, we are going to substitute. N substitute చేస్తాం, m into v equals to
Sir, E.
m into v equals to p, momentum of the particle. The product of mass
Yes,
and
sir.
velocity gives the momentum. So we are getting the equation for lambda in terms of momentum. After getting the equation in terms of momentum, to derive the equation for lambda in terms of kinetic energy, we derive the we find the relation between the momentum and kinetic energy. What is the relation between the momentum and kinetic energy? P equals to root over 2me. By substituting P equals to root over 2me, we get that equation lambda equals to h by root over
H by
2me.
under root.
h by root over root 2me. అక్కడ వరకు రాయాల్సి ఉంటుందమ్మా. ఓకేనా? ఫర్ ద ఫోర్త్ వన్.
Okay.
Rule number 8. 8, are you there, Amma? Rule number 8. Not audible, Amma. Your voice is not audible. Rule number 8. I think having mic issue. Keep one text message in the chat box, Amma. Are you there or not? Please keep one text message in the chat box. 8. Okay. Okay, no issues, Amma. Rule number 9.
Sir,
Yeah, 9. So tell me the read the fifth one.
determine an expressions for the wavelength associated with an electron accelerated by a potential V.
Continuation of the derivation. We derive the derivation part of de Broglie hypothesis. Na? So in the de Broglie hypothesis, up to in the fourth question, we discussed up to derive the equation for wavelength of the matter waves or wavelength of the electron in terms of potential. So how can you determine the expression for the wavelength associated with that electron accelerated by a potential V? So by taking one particle here we are taking one particle. How the particle will accelerate it? By applying some force on the particle or on body, it will accelerate. Here also in the periodic potential field, when the potential is applied on a particle, the particle will accelerate. When it is accelerate, that particle having kinetic charge and applied potential. Capital E equal to small e into capital V. Capital V is the kinetic energy equal to charge of the particle E and applied potential capital V. So already we derived the equation for lambda in terms of kinetic energy, that is lambda equals to h by root over 2me. So in place of capital E, by substituting small e into capital V, we derived the equation for wavelength of the electron in terms of applied potential. But we know the values of mass of the electron and charge of the electron. So by substituting that mass of the electron and charge of the electron, we simplified that equation by substituting the Planck constant value also. So then we are getting the equation for lambda in terms of potential in case of electron is 12.26 angstroms by root V. Okay, now that is also small answer one only. So fifth one, lambda equals to 12.26 angstroms by root V. How can we derive that equation? We are explaining. So rule number 10. Rule number 10, Amma.
Yes, sir.
Amma. What is the sixth one, Amma? Read the sixth question.
Why matter waves are observed for particles of atomic or nuclear size?
Amma? This is a general question. That's why I am keeping in red color. Why matter waves are observed for a particles of atomic of nuclear size? So let me know, Amma. Any one of you
They
have
are not
prepared the answer?
visible.
Amma?
Sir, they are not visible. So
Yeah. So if the question is asked for the two marks, how can you answer for that question? Only that point only you mentioned.
no, sir.
Then how can you answer for that question in your examination? Tell me, Amma, rule number 10. What is the name?
Akila, sir.
Akila. Amma, Akila. All line. Why matter waves are observed for a particle of atomic or nuclear size? All of you, remaining students also, please prepare the answer for that question. Or remaining all are we discussing this. For this one also we discuss some points in the class, but keep that points in order and make a answer for that question.